All right, so we're going to wrap up section 4.3 with a couple of examples of solving homogeneous linear differential equations with constant coefficients, where the order of the equation is higher than 2. We've been focusing on second order equations, but at the end of the last video, we talked about how those methods generalize really nicely to the higher order case. So let's start with this one. This is a third order DE. Linear, homogeneous, it's got constant coefficients 1 and -1. And the idea here is the same as what we did in the second order case. So we want to come up with that auxiliary equation. In this case, it would look like m cubed minus 1. Remember that y gives us a constant term. So this is m cubed minus 1 equals 0. Now, again, really this kind of just reduces to an algebra problem. But as you might remember from algebra, once you get past second order polynomials, or second degree polynomials, you start looking at cubics and quartics and stuff like that. They can be a little trickier to factor. So this is where you have to think back on some factoring techniques that you may have forgotten about. But this is what we call a difference of cubes, and it factors in a specific way. In this case, we're going to have m minus 1 times m squared plus m plus 1, and that equals 0. Okay? Now, again, this is from the difference of cubes factoring technique. This factor is going to give us one solution of m equals 1. This factor is not factorable, so we would have to apply the quadratic formula to that. We'll get m equals b squared, so it's -1, plus or minus the square root of, not b squared, negative b, plus or minus b squared, that would be 1, minus 4ac, that's minus 4, all over 2a, that's 2. This would be equal to -1/2, plus or minus, that's going to be a -3 in there, which is where we get the imaginary constant I. This is going to look like root 3 over 2I, okay? So that's a total of 3 roots. One of them is real, 2 of them are complex, and it's a conjugate pair as usual. Taking the results of what we did previously and putting that together into a general solution, we're going to get y equals, remember this first solution that we got here is going to lead to this c1 e to the 1x, let's just call it x. These conjugates, this complex conjugate pair here is going to give us solutions of this type, c2 e to the ax. Remember, a is -1/2, so let's call that -1/2 x, or x over 2. Cosine of bx. Remember, b is root 3 over 2, and even though we can make it positive or negative, you get the same answer regardless. So we're just going to go with positive root 3 over 2 x plus c3 e to the -x over 2 sine of root 3 over 2x. That would be our general solution, okay? And even though it's kind of a somewhat messy looking general solution, it's not the worst, getting it was relatively simple. It kind of just boiled down to knowing how to solve a polynomial equation. Not terribly difficult. This next example here that we're going to look at is going to be an IVP. So for this one, we have another cubic polynomial. We need its auxiliary equation. This one's going to look like m cubed plus 2m squared, okay, minus 5m minus 6 equals 0. Okay, now there's only a couple of techniques that we learn in algebra for factoring cubics. It's not a sum or a difference of cubes like what we saw previously. Factoring by grouping, you might remember doing that in algebra. That doesn't work here either. So it seems like a lot of the typical techniques aren't going to work, but this is a case where we want to use something that you may have learned in either pre-calculus or intermediate algebra, something we call the rational root theorem. The rational root theorem says that if we are going to have a polynomial with like a polynomial of this kind here, and if we expect to find a root of this polynomial that's also a rational number, then there's a very limited number of possibilities that that root could be. And the root can only equal a rational number that's equal to some factor of your constant term over some factor of your leading coefficient. So factors of 6 over factors of 1. That only leads to the following possibilities. M could possibly equal plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. These are all the possibilities that I could get from putting a factor of 6 over a factor of 1. Now, how do you verify this? That's still 8 possibilities. How do you check these? You could plug them in directly and see if they satisfy this equation, but usually in the rational root theorem, we use the faster approach of synthetic substitution. So I already know which one's going to work. Instead of doing a whole bunch of trial and error, I'm going to save us some time. If I put 2 is one of those possibilities here. Synthetic substitution or synthetic division is the algorithm that we're using. I write the coefficients of my auxiliary equation, 1, 2, negative 5, negative 6, 1, 2, negative 5, negative 6. And then I proceed with synthetic division. If you remember how this works, we drop this 1 down here. We do 2 times 1, which gives me 2, and then I add. 2 plus 2 is 4. 2 times 4 is 8. Negative 5 plus 8 is 3. 2 times 3 is 6, and negative 6 plus 6 is 0. This thing in this little box that I made here is called our remainder term, and if we are going to get an actual root of this equation, an actual 0 for this equation, then we need this remainder to be 0. So that's what we're looking for. We got 0, which means we've got what we wanted. What does that tell us? It tells us that this equation here, the left-hand side, will factor as follows. M minus 2. This comes from the fact that I used a 2 here. 2 is a 0 of that factor. And then the coefficients of the quadratic term or factor that's going to end up here comes straight from the division down here, 1, 4, and 3. That becomes 1m squared plus 4m plus 3, that would be my constant term, equals 0. And that factors nicely. So I have m minus 2, m squared plus, oh, sorry. I was just rewriting what I did already. M minus 2, m plus 1, m plus 3 equals 0. Okay? Now, this means that we have 3 solutions. So I have m equals 2, negative 1, and negative 3, giving me the general solution. These are all distinct real roots. I have no repeated roots, no complex roots. This gives me the general solution, y equals c1e to the 2x plus c2e to the negative 1x, or just negative x, plus c3 e to the negative 3x. Okay? Now, we're not done because this was an IVP. We have initial conditions that we have to worry about. Up here, it says that y of 0 and y prime of 0 are both equal to 0. So in order to use that y prime and to use the y double prime that's also showing up as an initial condition, I would need my first and second derivative of this. So what does y prime look like? 2c1 e to the 2x minus c2 e to the negative x minus 3c3 e to the negative 3x. And then what about y double prime? Y double prime is equal to 4c1 e to the 2x plus c2 e to the negative x minus plus 9c3 e to the negative 3x. Okay? Now, according to our initial conditions, if we plug 0 in for x, so we have y of 0, y prime of 0, and y double prime of 0 showing up as our initial conditions. Y of 0 is supposed to equal 0. That implies that 0 is equal to, plugging 0 in for my x's up here is just going to give me c1 plus c2 plus c3. This one of our initial conditions said y prime of 0 equals 0. That implies that 0 is equal to, again, plugging a 0 in for x's up here, it's going to give me 2c1 minus c2 minus 3c3 just minus 3c3. Y double prime of 0 is equal to 1. That's going to give me 1 equals 4c1 plus c2 plus 9c3. What we have here is a system of 3 equations and 3 unknowns. We can solve this system. Okay, most of the time I wouldn't go through the trouble of solving this by hand because it's technically just algebra and it's time consuming, but it may, depending on whether you've had linear algebra recently or not, you may have, it may have been a while for you since you last solved a system of 3 equations and 3 variables. So I'm going to just take the time to work through this one, and then in future examples we probably won't go through all this work. Okay, so here's my system up here. What I'm going to do is start by adding this first equation to the second equation, because what that will do is eliminate that C2 term. Okay, so if I do that, I'm going to get 0 plus 0, which is 0, and that will equal C1 plus C1, which is equal to 3C1. These terms cancel. Adding these give me minus 2C3. Then I'm going to add the second equation to this third equation because once again, the C2s will cancel out. That's going to give me 1 equals 6C1. Those cancel. And this is going to add up to plus 6C3. Okay? Now for the sake of eliminating another variable here, I can multiply this top equation by 3, and then add the results to this equation. So 3 times 0 is 0, plus 1 would be 1. 3 times 3c1 is 9c1, plus 6c1 would be 15c1. And then 3 times negative 2c3 is negative 6c3, plus 6c3, that cancels, which was the whole point. So this means that c1 is equal to 1/15. Let's plug that in to say this top equation here to solve for C3 now. Okay, so this implies that 0 is equal to 3C1, or 3 times 1/15, which is 1/5, minus 2C3. Okay? Solving that for C3, and add 2C3 over and divide by 2, C3 is equal to 1/10. Okay, now I have 2 of my unknowns. Let's go to one of our original 3 equations, maybe this top one up here. Plug in the values that we got, solve for the one unknown. So that means that we have 0 equals C1, which is 1/15, plus C2, which we don't know yet, plus C3, which is 1/10. Okay, 1/15 plus 1/10. If I got a common denominator, that's 2/30 plus 3/30, or 5/30, which is the same thing as 1/6, making C2 equal to negative 1/6. Okay, so putting those 3 things together into our general solution up here, I get, I'm going to go like this, so that's back on the original page. My general solution is going to look like y equals C1, which was 1/10, e to the 2x, plus C2, which was negative 1/6, so minus 1/6, e to the negative x, plus C3, which was 1/10, e to the negative 3x. And that's our final solution. Okay, that's going to wrap up section 4.3.